The chemical properties of elements in the periodic table are periodic, not because of some random thing, but because the valence electrons of the different atoms are periodic. We observe that elements in the same column have similar properties and that elements in a period show a pattern that repeats. The quantum mechanical model explains that this occurs because the number of valence electrons and the types of orbitals that they are in also are common in the groups of the periodic table, and they repeat in patterns. So if we look at the noble gases, column 8A in the periodic table, and this little inset here is showing us the valence electrons for these noble gases. And what do you notice about these configurations here? Yeah, the group number, the period number, this was period 1, 2, 3, 4, 5, 6, the rows in the periodic table, and the principal quantum numbers here are both increasing by 1. And all of these have whichever principal quantum number, S2, P6. That's a full valence shell, right? And their electron configurations are very similar. It's just they're filling up higher and higher levels. All of the noble gases have 8 valence electrons except for helium. He's a little baby guy and he's too little. So he's got 2 electrons, 2 valence electrons. But that smallest shell only holds 2 electrons. And so his valence shell is full. And that's the key. The noble gases are very unreactive because they have a full valence shell. Having a full valence shell of electrons is a minimum in the energy curve. And so it's like rolling down a hill, everything stops at the bottom, right? And so this is a lower energy place, and it's a good place for the atoms to be. Now, in chemistry land, these are the cool people from high school, that in-group that lots of people were trying to look like, and they would dress like them. When my son was in high school, it was Hollister hoodies. And you go to, drop them off at school, and everybody was wearing a Hollister hoodie. And it's like, this was, no, it wasn't really, it was a manual, actually, a manual. Pardon me? No, I'm not. No comment. This is being recorded. But they all just, they wanted to look the same. This is the group of kids that everybody wanted to look like. Okay? All the other elements are trying to achieve this sort of an electron configuration. I think of the number of protons in the nucleus of an atom as being like its soul, its personality. That cannot change. You can't change who you are. The electrons are on the outside of the atom. They're more like your hair and your clothes and stuff you carry around with you. And you can change that. You can make yourself look very different. And atoms do that too. And so they're going to change the number of electrons that they have so that they can look like a noble gas. Okay, so that is not a scientific explanation, but it helps us remember stuff. And it's kind of crazy, and that helps us to remember too. Yeah, so I think I said everything on there. So if we go to the other side of the periodic table, group 1A, how many valence electrons do these guys have? 1. Let's think about lithium. Lithium has 1 valence electron in that second energy level. What is underneath that second energy level? The first energy level. Yeah, it wasn't a trick question. And the level underneath is full. Lithium has 3 electrons. We can tell from the number 3 above his symbol there. Helium has 2 electrons. Helium is a noble gas. Helium is one of those cool kids. And lithium is thinking, man, if I got rid of this 1 electron, I would look like helium, right? And that would be good. Lithium, the atom, is likely to lose an electron because when it does that, it then has a full valence shell, which is lower in energy, and that's a good thing energy-wise. So these alkali metals are very close to the noble gases in terms of number of electrons, and they can attain a noble gas configuration by losing one electron. So this statement here is talking about more than just this group. These guys just need to lose one electron. They have one electron more than the previous noble gas, so they will lose that fairly easily and form +1 ions. When they do that, like when sodium loses one electron, it now has 10 electrons. That's the same number of electrons as neon, and they're going to be arranged in exactly the same way. So these metals are very reactive because it doesn't take much to get them to give up that electron. The halogens are one column over from the noble gases the other way. We look here at their electron configurations. They've all got 7 valence electrons. The principal quantum number, S2P5. They need 1 electron. You're thinking, man, if I could just get a hold of 1 more electron, chlorine, sand, if I could just get a hold of 1 more, I would look like argon, and then my life would just be sweet, right? Everything would be great. I was going to say hunky-dory, but that would really date me. So the halogens are also quite reactive. They tend to gain 1 electron to get the next noble gas configuration. And so they form anions with a 1- charge. This is explaining the behavior that had been observed of how the halogens form -1 ions and the alkali metals form +1 ions. We can predict the charge for main group metals and nonmetals based on their position in the periodic table. And this goes back to their electron configurations, but group 1A forms +1, group 2A +2, group 7A 1-, because they gain 1 electron. And the group 6A will form a 2- ion, because if it gains 2 electrons, it can become like the noble gas. So they're doing this in order to get an electron configuration the same as a noble gas. This is a figure from the textbook, and there's I had to correct this because they numbered their periods wrong. They forgot that hydrogen's not on here, and so they started numbering at the top. I don't know why I see these things. I can't help it. So here's the cool people column. This is where everybody wants to be. Fluorine, chlorine, bromine, iodine. By getting 1 more electron, they can join that club. These guys need to gain 2 electrons. Nitrogen needs to gain 3. Over here, it's the fastest and easiest for lithium to lose an electron. All the group 1As lose 1, group 2As lose 2. Aluminum's going to lose 3 valence electrons to become like neon. Now what about group 4? We're not seeing any ions in there. Group 4 is halfway between. Carbon is up here. Carbon really doesn't form ions. It would have to either gain 4 electrons or lose 4 electrons, and that's just too hard. And so carbon does not become like a noble gas by becoming an ion. It just doesn't. We can look at the electron configuration of anions. These end up being actually pretty boring because they all end up being noble gas electron configurations. So if we look at sulfur, here's the electron configuration for sulfur as an atom. It has 6 valence electrons. When it forms an ion, it's going to gain 2 electrons and fill up this shell. So it's going to be S2P6. We have to put a 2- charge on that. And that's the same as the electron configuration for argon. So that equals argon. And all the anions will do that. They gain to fill up the valence shell. Cations will lose their valence electrons. So here's magnesium. Magnesium has 2 valence electrons. It could conceivably gain 6 electrons to become like the next highest noble gas, but it's easier to lose 2 than gain 6. And so it's going to lose these, and now it's just got 10 electrons, and that's the same as neon. When you have two species that have the same electron configuration, we say they are isoelectronic. They have the same number of electrons in the same arrangements. This process is always endothermic, meaning it requires energy. I sometimes talk about, magnesium wanting to get rid of 2 electrons. But the fact is, he's not going to give them to you for free. You have to pay him for them. So you do have to expend energy to pull the electrons off. So anytime you form an ion, it is an endothermic process. I was just wondering if I missed something like that on that slide. I did not.